Okay, here we have lesson 2 of radical functions, and this one is quite a bit more complicated. So basically what we're doing here is we're taking a function we're given, and we're taking the square root of it. Now we're asked to do this from the equation, which is relatively simple, but we're also asked to do it from the graph. So we're going to be given a graph like this, and say, give the square root graph. Now it's easy enough when you know the equation to sketch it, and what will actually end up happening is you'll get something that looks like this. So if you want to step through the investigation, you can. I'm not going to. I'm going to skip kind of straight to the pattern and the rules. But you could take turns graphing the top one and graphing the square root graph, comparing the domain and the range. You could step through that to try and investigate the properties that are listed here if you like. And I'm just going to skip to the summary of them because I know that you can graph them. So this is a continuation of the summary here. So what are our rules here? When we're graphing the square root function, so in a way we're considering this a transformation now. We are changing a function we're given by taking the square root of it. So the very first thing we always need to remember is when our original function f of x is less than 0, the graph of y equals f of x does not exist. Well, why is this? We know we cannot take the square root of negative numbers. So where f of x has negative y values, or negative outputs, we cannot square root them, so therefore this graph doesn't exist. Then we have sets of invariant points, and these are kind of the key to giving these sketches. We know that the square root of 0 is 0, and the square root of 1 is 1. So what this means is when f of x is 0, the square root of f of x will also be 0. And when f of x is equal to 1, the square root of f of x will also be 1. These help us because we oftentimes will start by plotting these invariant points, and then it's kind of a game of connect the dots once we know where our domain and range is. When the original graph f of x is between 0 and 1, the graph of y equals the square root of f of x lies above the graph of y equals f of x. Why is this? Well, the square root of 1/4 is 1/2. So what this is saying is when we take the square root of a number that's between 0 and 1, we actually get a larger number. The square root of 1/4 is actually bigger than itself. For any other number, that's not true. Square root of 4 is 2. The square root is always smaller. So for when f of x is greater than 1, the graph of y equals f of x lies below the graph of y equals f of x. The values of the square root f of x are the square roots of the values of f of x. So this means we square root the y values of our original function to make our new function the square root of f of x. So if possible, choose values of f of x which have simple square roots. If the graph of y equals f of x has intervals containing oblique straight lines, so that word oblique just means like diagonal, straight lines, the graph of the square root of f of x will be concave down on those intervals. So let's put this all together with these couple examples here. So the graph of a function y equals f of x is shown. Sketch the graph of the square root of f of x on the grid. So what's often simplest to do is start by putting in some invariant points. So whenever our y value is 0 or 1, those points are going to be on our square root graph as well. Okay. Whenever the graph is below the axes, I'm not going to have a graph. So right here, this graph is less than 0, so I'm not going to place any part of my graph to the left of x equals -3. Now I can calculate some easy to calculate points before I start sketching. So this value is 4. If you look at some max and min values, it becomes simple to look at. So this value is 4. The square root of 4 is 2. So I know that this straight line is going to now, instead of being at 4, it's going to be at 2. And this maximum point is at 2, while square root of 2 is 1.4 something, so it's going to be about there. Now, from here to here, so this is the first segment we need to look at, from x is negative 3 to x is negative 1. We see for this portion, we are looking at values less than 1. Well, values between 0 and 1 we know need to be above f of x. Everywhere else it needs to be below. So that means for this section I need to be above. For this section I need to be below. And since this is a straight line, it tells me that I need to concave down. So I draw my section concave down. I'll go over it in a color, so I did lots of scribbles so you kind of know what I was talking about, but I'll do the actual graph in yellow here. So in this section here, the original graph is below 0. Sorry, the original graph is not below 0, is below 1. So that means I need to be higher than it. Here, for after that, the original graph is greater than 1, so I need to be below. So I'm going to keep going here, and I'm going to keep concave down because this is all straight pieces till I get here again. Well, here again, my function has value less than 1, so I need to make sure my square root is above it. Looks something like this. Same thing here, I'm going to be above the graph. This should be more of a continuous curve to this point. And then back down. So wherever I am in this section of the graph between 0 and 1, y values of 0 and 1, I always need to be higher than the black line with my yellow. In all the other sections, I'm beneath it. So what is the domain of f of x? Well, the domain of f of x was any real number. That was the original. The square root of f of x, well, I started here at negative 3, and I ended here at 16 because that's when the y values went negative. So it is from negative 3 to 16. Sorry, I wrote that in the range spot. Negative 3 to 16. The range of the original was a maximum number of 4 all the way down to negative infinity. And what is the range of the square root graph? Well, the square root graph, this maximum point here is 2, and the minimum point is 0. So 0, 2. It takes some practice. The most important part and the most questions are asked on those invariant points. You'll see questions that'll say, how many invariant points are there? All you have to do is count the number of times that original graph has a y value of 0 or a y value of 1. In each case of the graph of g of x, if h of x equals the square root of g of x, determine the domain and range of h of x without sketching. Okay, so looking at this first graph, the original domain is all real numbers, and the range is all values greater than 3. Well, since this graph has no negative y values, the domain here is also x is all real numbers. The range is a little bit trickier. Remember that for the range, we square root all the y values. Well, our smallest y values here were 3. Those will still correspond to our smallest y values, except now we've taken the square root of them. So now our smallest y value will be the square root of 3. B. Okay, B is a little bit trickier because it has sections of the graph that are beneath the x-axis. So for those portions of the graph, we do not include them in the domain of the square root function. So our domain here will consist of different segments. We will go from, there's no arrow here, so it stops at negative 3. So we will have from -3 to -2, and there's two pieces. We would have this section from 3 to 8. So you can write it with an and or a comma. It's just showing that there's two sections of it. The range, well, we can't have a y value less than 0, but we do have some y values of 0. So those points will stay there, right? These 3 points will be invariant. So we know 0 will be our smallest value. What'll be our greatest value? Well, we find our maximum value and we square root it. So our maximum value would be the square root of 9, which is 3. So the range in this case is between 0 and 3.